All right, let's get started. So in the last class, we ended up talking about the standard penetration test. So before we jump right back into things, let's do a quick recap of what it is. So the SPT is essentially a dynamic penetration test used to evaluate any geotechnical properties in situ. So in situ more or less means in the ground as is, right? So if you, we can use this schematic here just as a quick refresher. So as the name specifies, standard penetration test, everything is standardized, including the mass of the hammer, the height to fall, and also the split spoon or split barrel involved. I know some of you have concurrent exams today, so we will record the lecture and post it onto Moodle for you. There's a midterm. I'm not sure if the student meant the midterm's concurrent or they have to study for the midterm, but either way. So anyhow, so with the standard test, penetration test, there are two drives. You have the seating drive and the test drive. The seating drive is 150 millimeters. So this is the seating drive, and then the test drive is 300 millimeters. And we take blow counts every 75 millimeters. Blow count is specified as N. Each time you bring the hammer up and drive it into the split barrel, then that counts as one blow. We also talked about how there are termination criteria. It more or less depends on what type of project you're dealing with. Generally, we assume that the termination criteria is about 50 for the seating drive and 100 for the test drive. What's interesting is, even in Hong Kong, there are different termination criteria for different projects. If you're working on a housing project, ASD project, GEO project, you may encounter different termination criteria. So then the question is, how standard is the standard penetration test? It can be quite confusing if you're interpreting N values from different tests using different termination criteria, right? Later on, we'll do some examples of the SPT test, and then you can get a better understanding of what this so-called termination criteria is. And the termination criteria, of course, is to prevent the damage of equipment and prevent meaningless hammering of the split barrel into the ground when you can no longer penetrate it because the ground is too stiff, or you've encountered large or hard inclusions such as core stones, right? So back to our SPT test. So in essence, we take how many increments? Well, the seating drive is 150. 150 divided by 75 is 2 increments. And then we take 4 increments. So there's 2 increments here, and then there's 4. So you take about 6 increments of blow counts. Again, when we look at the log for SPT testing, it'll be more clear what's going on. And we mentioned that when we carry out SPT testing concurrently, we have the advantage of obtaining some sort of soil sample on the ground. And this soil sample, although highly disturbed, can be used for simple indice testing and classification. You can also use it for PSD and also moisture content. So this is a quick overview of what we discussed in the last class. And we ended off here with these few points. So in summary, what I just mentioned, SPT tests are quite ideal for granular soils to determine the in situ strength. And we'll talk about how to determine the in situ strength based on the N value later on. There are significant volumes of literature and correlations in Hong Kong, because in Hong Kong, we are quite data rich, right? And we're quite dense. We have lots of geotechnical works, so we have lots of data to use to correlate with friction angles for cohesionless soils. And as I mentioned, the standard drop mass is about 63.5 kilograms or 140 pounds for the hammer. The drop height is about 30 inches or 0.7 meters. And we use standard split samplers, split spoon or split barrel samplers that allow you to obtain a soil sample. So once you extract it from the ground, you open up the split spoon and you can take a look at what's inside. The total distance that we travel is 450, right? 150 for the seed drive and the 300 millimeters is for the test drive. And mentioned here, we have 3 consecutive penetrations, if you count it as that. We only take the N value from the test drive. So the N value is mainly derived from after you complete the seed drive. In the test drive, you want to penetrate 300 millimeters, and you record how many blows it takes to reach 300 millimeters. And that constitutes your N value for a particular test and sample. The N value, besides strength parameters, can also be related to soil classification, relative density, soil consistency. So there's a wide range of parameters that this N value can be used for. And we mentioned termination criteria, often 50 for seed drive and 100 for test drive. And last but not least, we obtain a highly disturbed sample. So for some projects in Hong Kong, for instance, ASD projects, we have these are the termination criteria. So the seeding drive, is 50, and the test drive is 100 for the termination criteria. These are N values, okay? For housing projects, seating drive, we can just have one N. So seating drive is 50 blows, and the test drive can be up to even 200 for some projects. So you have to be conscious of what type of project you're working on. Is it an ASD project, housing project, geo project, and termination criteria may vary. So that's where we ended off in the last lecture. But to give you more context, it's probably easier to show you photographs of what an SPT test looks like. And we routinely carry out these tests in Hong Kong. Here at the top photograph, you see a technician carrying out the SPT test with a hole or donut hammer device. So this is your hammer. It's essentially, there's a hole in it, and it gets lifted along a particular rod to specified height and dropped onto the anvil. And somewhere down in this hole is the split spoon sampler that we talked about. If you want to have a better image of how the split spoon sampler looks like compared to what I tried to draw, this is how it looks like. You can split this sampler in half and you get highly disturbed samples. You can imagine it's highly disturbed because we're trying to force the soil into the sampler dynamically, right? So there's no hope of carrying out any intact tests for odometer testing or intact triaxial specimens. Normally in geotechnical or ground investigation, we have something interesting called the area ratio. The area ratio is very simple. It's just the outer and difference between the outer and inner diameter of your sampler. Normalized by the inner diameter, and what happens is you get some sort of ratio. We call this the area ratio. Anything less than 10%, we would consider it undisturbed sample. So it's actually very difficult to get an undisturbed sample. You can see here when you carry out SPT testing with a split spoon sampler, you have almost 100, in excess of 100% area ratio. What's an example of undisturbed sample that can give you less than 10%? Well, when we carry out land reclamation, we have other types of samplers that we can just push into the ground. We have these push-in piston samplers. These have very low area ratios, about 10% or sometimes even less. So those are examples of undisturbed samples. And undisturbed samples, what can you do with it? Well, you can take it, extract it, extrude it from your Shelby tube, for example, bring it to the lab and do direct odometer or traxial tests. And obviously you can't do it in this case here. So this is a general schematic of how SPT testing looks like. If we show you a few more schematics, it might provide you with a bit more clarity. So on the left side here, we see a cross-section of our split spoon sampler. Of course, it's more complex than what I showed you, a cylinder cut in half. So when we're talking about the area ratio, we're basically comparing, this is the inner diameter, and then you have outer diameter. So there's a certain thickness, a wall thickness to your sampler. And the thicker your wall, the more disturbed your sample will be. That's just how it is. You can imagine that when you drag this sampler downwards, the soil will move inside here, and there's usually a ball check valve to allow air to extrude out of the sampler. Otherwise, it'll be difficult to get more soil inside, right? And that's a typical cross-section of a split spoon sampler, the standard size one, about 35 to 36 millimeters in diameter. If we treat that as an inset, normally what we do is we connect some rods that are about 32 millimeter boring rods on top of this. And on top of these rods, we connect the hammer and anvil device. These days, we use automatic hammers, so we don't rely on a worker pulling back on some sort of pulley device and releasing the rope. Release this 100 times probably. So it's automated. And this is an example of an automatic free drop trip hammer, also known as the monkey. So this is the entire setup and cross-section of SPT. If you want to look at something more old school, it still happens. Then we have a pulley system with a rotating cat head and some technician involved. And he has to do this until he reaches the penetration of 300 millimeters. So you can imagine there are a few problems with this setup, right? If you have a different height of technician, he might pull the cat head differently. If you wrap the rope differently in a different direction, or you pull at a different angle, you might have different energy losses, right? Although we say it's 30 inches, but there's energy loss in this entire system. So you can probably imagine that although we want to input a theoretical amount of energy, we're not actually getting this out because we're losing energy as well. So it's often quite confusing to interpret N values in the field. I think most of you are doing a capstone project where you look at GI logs, right, for the geotechnical team members, and you see N values, right? Often these are not N values. You see them called N60 values. Some of these are even called N160 values. The one is mostly for seismic related topics, but you might even see N160 as well. Just different names for what we treat as a standardized N. What does that mean? Well, if we try to use the raw N values, you can get differences of up to 2 times for the same project, because some technicians will use different setups, different hammers, they have different heights, they pull up this cable in a different way, and they don't account for energy losses in the system. Where are the energy losses coming from? Well, it comes from the deformation when you smash the anvil. You have compression waves moving up and down the rod, deformation of the setup. So often we use a reduced N, and we call it N60 to account for these energy losses. And we'll talk about how we accommodate for energy losses in a bit. Okay, so there are, in essence, 4 corrections that we should make to obtain our N60 value. So the N60 value is our corrected value. Now, the first issue that we often encounter when doing SPT testing is energy loss due to heat and noise dissipation. We also have bending of the rod, bending of the anvil, bending of various components. So it's recommended, if you want N60, the corrected N value, we have to consider the length of the rod. Now, the longer the rod, the more energy is dissipated, right? The shorter the rod, the less energy that's dissipated. So this is reflected, and you can see on this line here, if you have a rod length that's greater than 10 meters, then you take a discount of 60%, right? And if you have a rod length less than 10 meters, then you only have to discount it 25%, sorry, 40 and 25%. So you can maintain most of the more energy if it's a shorter length, right? So we have to apply various correction factors to our obtained raw N values for the last 300 millimeters of penetration. Now, aside from energy from noise, heat, deformation of the device, what else do we have to account for? Well, we also have to account for the effective overburden. Here you see 6 and 1 used. Let's just assume it's N60, but we don't need to be too specific about this. So as you get deeper into the ground, there's higher overburden, right? We know that stress is equal to the unit weight times the depth. So how do we compensate for increasing confining stress as we move in the ground? Well, there's a correction factor for increasing stiffness as well. There's 2 ways to look at it. You can look at it in terms of this graphical approach where you can say, look, this is my effective overburden pressure, and I can relay a C subscript N value of this graphical approach, or we can just use the Lau and Whitman 1986 equation here to calculate what the Cn should be. So to this point, there are 2 corrections required. You have rod length and overburden. And normally when you look at a GI report, such as your capstone project, these N values are corrected already, right? You get N60 values in the GI reports, if you notice. So it's nice here to know what's being corrected here. The next element we do have to consider is the effects of borehole diameter. In research, we find that lower N values are obtained in 150 and 200 millimeter boreholes, which are standard borehole sizes, compared to those using 115 millimeter diameter boreholes. Now, but with this knowledge, we should apply some sort of correction for the effects of borehole diameter. And that's what you see here next, C subscript B. We have the borehole diameter correction factor. Depending on the size of your borehole, you apply different values. And this, of course, is semi-empirical, right? So you have 3 diameters here. If you have diameter from 65 to 115 millimeters, then you apply no correction, right? Unity means no correction. If you have a diameter 150, then you will have to augment your N value. 1.05 means you're increasing it. Likewise, if you have a very large diameter borehole, then you have to increase it by 1.15 times. So this is the 3rd correction we do. The last correction we have is the effects of the rod length, but it's dissimilar to A. We're talking about the time for transmission of stress waves when the SPT hammer hits the anvil and transfers the energy to the slit spoon. So we call this correction factor C subscript R, and it's quite straightforward. I don't expect you to know the details, but I'm sure the procedure here is quite straightforward. Even if I gave you this slide, I think you can correct it quite easily. So for CR, you can see that for different lengths of rods, here's less than 4, 4 to 6, 6 to 10, and above 10, you don't have to correct. But anything less than 10, you have to reduce your N value accordingly. So how do we correct for a holistic N60 value? Or you can have N160. For me, and for this class, there's no big difference. You can get a generalized correction by just multiplying the 4 correction factors, C subscript E, C subscript N, C subscript B, and C subscript R, by your measured N value from the 300 millimeters during your test, right? So these are the values we often use to communicate as geotechnical engineers. We rarely use the N values that are raw because they can vary by a factor of 2. If we don't cater for all of these effects, we have to consider any corrections to the N value. So in case you're reading the GI reports right now for your capstone, you're not sure what's happening with these N values. Well, that's exactly what's happening. They're being corrected to account for various energy dissipation, stress wave propagation, borehole diameter, and the effects of overburden. So that's what N60 is. Now, we often correct the N60 after we get the N values from the field. But let's jump back to SPT test. How do we interpret SPT lab report or field report data? Well, this table is quite important because it helps us to understand what's happening during the SPT test. So let's look at this one example at a time. Now, we have 2 drives. Remember, seating drive is 150 millimeters, and this can give us 2 75 millimeter increments. So what does that mean? We take 2 N values for the seat drive, right? And then the test drive is 300 millimeters, right? So we can take 4 75 millimeter readings. We take blow counts every 75 millimeters of penetration. So let's take a look at what's happening. So let's take a look at the first example here at the top, row number 1. So I'm guessing the termination criteria here is, so for the seat drive, the termination criteria is 50. And for the test drive, the termination criteria is 100. And this is the blow count. So we don't exceed this. Now, first row, what's happening? So seat drive, we want to penetrate 150 millimeters. So to penetrate the first 75 millimeters, it only took 17 blows. And to penetrate the next 75 millimeters, it only took 25 blows. And combined, you get 150 millimeters. And just as a refresher, why do we do a seat drive? Well, normally for SPT testing, we have to drill down to the depth that we're interested in. And drilling causes a lot of disturbance to the soil, causes remolding. So what we want to do is initially, we don't want to work with the soil that's very close to where the drill was, because some drills even have flushing, right? You flush with water, high pressure water. So the soil near the bottom of a borehole, let's say here. So normally, even if you have an auger and you drill down, you can even have flushing as well, flushing fluid. So the soil here, just at the base of your drill hole, can be highly disturbed. That's why we often do a seat drive to get our sampler just slightly past this highly remoted part. No matter what you do, it's highly remoted, okay? And the sample that you get is highly disturbed, but the seat drive is just an extra precaution. So after the seating drive, what happens? Well, luckily for us, we reached the 150 millimeters, right? and we didn't have to reach the termination criteria. If you had 25 and 25, then you would have reached the termination criterion for the seeding drive. And then you would have to stop and then proceed with the testing drive, right? But in this case, the seeding drive worked out quite nicely. Now, for the test drive, what's happening? Well, for the test drive, it's actually very smooth as well. Not a lot of problems. For the 300 millimeters, the first 75 mm only took 25 blows. Likewise, the next 75 mm only took 27 blows. The next 75 only took 22 blows. And the last 75 mm took 23 blows. So if you add up these four 75 millimeter increments, you get 97. So that's less than 100. So you never had to terminate at any point, right? So then your N value for this soil, or at this depth here, would be 97, because we only take the accumulated blow counts for the testing drive, right? So in some remarks, you would see full penetration. You ran into no problems at all. Let's take a look at the next example together. So again, you have the same situation as the first case. For the first 75 mm, you took 17 blows, and for the next 75 mm for the seeding drive, it only required 25 blows. So exactly the same as the first case. And then you know that you can move on to the test drive. Now for the test drive, we have something slightly different here. For the first 75 mm, you require 38 blows, right? How about the next one? Well, the next one, you had 62. So what's 38 plus 62? That's 100, right? So that means you reach the termination criteria. What does that mean? Well, you're supposed to stop because that's the termination criteria. If you keep on smashing the split spoon, you're going to break something, or it's just futile. It's just wasting time on site. Or you probably encountered a hard rock or large rock or boulder or core stone in the ground. So what does this tell us? Well, for the second increment here in the test drive, we were only able to penetrate 50 millimeters. Now, for the first increment of the test drive, it's standard 75 millimeters, right? So what's 75 plus 50? Well, it's 125, right? So in your summary, you would say, look, for the test drive, our N value is 100, but we were unable to penetrate 300 millimeters, right? We were only able to get 125 millimeters of dynamic penetration. And the last remark says test terminated in increment for, well, this increment can be a bit subjective, but in their case here, as you'll see in the last example, it's a little inconsistent. What they consider as an increment is maybe this is 1, this is another 1, 2, 3, 4. So they say the test terminated in increment number 4. So that's the remark. Now, let's look at the next example. What else can happen during SPD test? Well, we have the exact same seat drive condition for the first 75 millimeters and the next 75. So the seat drive was successful. For the test drive, we required 35 blows to reach the first 75 and then 27 to reach the next 75. And we encountered some struggles for the third seat drive, test drive increment, sorry. For the third test drive increment, we required 38 blows to only penetrate 30 millimeters. Now, if you add this up, we would have reached our termination criteria. And where does the 180 come from? Well, the 180 comes from 75 times 2 plus 30. So we see here that The N value of our soil here would also be 100. And the note here would be showing us that we did not reach 300 again. We only reached 180 out of 300 millimeters during the test drive. And some remarks will tell you even what increments. In this case, 1, 2, 3, 4, 5. So the test terminated at increment 5. So let's look at cases where the seeding drive isn't so ideal. No, this is getting heavy. So let's look at this case now. So for the seeding drive, we have 27 for the first 75 millimeters, and then you have 23 for the next 75 millimeters. So what's happened here? You've reached 50, right? We mentioned that the termination criteria for the seeding drive is 50. So we shouldn't go any further. And for the second increment of the seed drive, you only achieved 35 millimeters out of the required 75. So you would just record it. You would stop. And what do you do after that? Well, you stop and you proceed with the test drive. You might be thinking, okay, if my seed drive can't penetrate it, what makes us think that the test drive will? Well, sometimes it does if you apply enough energy to the ground. So since we reached the termination criteria for the seeding drive, we progress with test drive. And surprisingly, the test drive works out quite nicely. So you get 25 blows for the first 75, 27 for the next 75, 22 and 23 respectively for the next two test drive increments. And if you add these four up, you get a blow count of 97. But these are uncorrected values, right? You would have to correct these later on, depending on what device you use to carry out the SP test. So the note here would say the test drive commences after completion of 50 blows, which was the termination criteria for the seed drive. And this was the achieved N value. So in our last example here, should be 4. For the seed drive, we cannot get even the second increment going. In the first increment, we can only penetrate 20 millimeters, and we reach the termination criteria 50 right off the bat. And that's what this means. And then we know automatically we should jump to the test drive. And for the test drive, we're getting some penetration here. So for the first 75 millimeters, 35 blows. For the next one, 75 blows. And for the next one, we have 38 blows, but we can't finish the 75. We only get 30. And if you add 75 times 2 plus 30, 180, and we reach 100. And the remark would tell us that the test drive commences after completion of 50 blows in the seeding drive, and we have the test terminated in the fourth increment. Or actually, is it? Yeah, it should be fourth increment. Here. So that's essentially how SPT data looks like. And I hope by looking at this log, you sort of understand how SPT testing looks like. Now, at this point, we've only talked about how to get these N values. What do we do with these N values? We talked about, yes, you have to correct it based on the device that you use, a donut hammer, rod length, portal diameter. But how do we use the N value? How do you use it for your capstone project, right? If you want soil strength parameters, well, normally a GI report will also have the elevation. And on the x-axis, you have the blow count. These are uncorrected values. And in this example here, you would have soil classification. And you can generally see that you can plot different SPT data from different boreholes. So you have two borehole here, borehole 1, borehole 2. Borehole 1 is, of course, the closed markers. Borehole 2 is open markers. And if you plot all the data here, you can actually do something that's very common in geotechnical engineering, is getting a strength envelope, right? Why do we want a strength envelope? Well, let's say you get some relationship here. Y goes mx plus b for linear relationship. Then let's say you're running classes. If you want to tell classes that your soil strength will increase with depth, then you can plug in a linear relationship, right? Or you can also say we have a uniform strength for this homogeneous layer, right? But normally we would consider the effects of strength increase with depth. And you can characterize the different types of soil type. That's how SPT data may be reported in some logs. Now, what do we do with the N values? So let's say we've corrected our N values to N60 values. There are a lot of literature where the N values are not corrected as well. So you need to be careful when you're interpreting N values. So we call SPT empirical approach. Why? Because the N value is something we measure, and we just roughly use empirical methods to relate it to soil strength parameters that we care about. There's no real mechanics or theory tying these two together. And we already mentioned there's no stress path, there's no control of drainage. So it's a highly empirical method, but it's a highly empirical method that's commonly used in Hong Kong geotechnical practice. We just think about what's the N value, and a very good geotechnical engineer will be able to tell you whether that's a strong soil or a very weak soil. So let's look at SPT correlations for cohesionless soils. Now, cohesionless soils are coarse grained soils, sands, gravels. Now, with SP value, in this table here, we have increasing density from very loose sand, medium sand, dense sand to very dense sand. Now, you can see the corrected N values here generally increase with sand density. Likewise, the relative density should increase with sand density, otherwise it wouldn't make sense. So you can use N values to deduce what the relative density of your soil is based on correlations. Where are these correlations from? Well, they're from the hundreds of geotechnical projects, thousands of geotechnical projects in Hong Kong. You take the data, you group it together, and you come up with correlations. And that's how we use it. Besides density, you can also get strength parameters. Of course, for these cohesion soils, we're interested in phi dash. And depending on different correlations in literature, this is evidently not Hong Kong data. You have Peck et al. In 1974, Meerhoff in 1956. The only real trend you can see here is increasing friction angle, or phi dash, with density. But the main point we want to stress is once you get your N value, you can use empirical correlations in the literature from past projects in Hong Kong to relate to useful design parameters. For example, we need phi dash in Plaxis analysis, we need phi dash in slope W. So this is how we get it. And of course, there are also well-established graphical approaches. Schmertzman here in 1975 provides a graph of what appears to be uncorrected blow counts versus the effective overburden. And the effective overburden, because you know what depth you're at. You can approximate the dry unit weight, or the unit weight. It's not too difficult. And you can pull off a friction angle for design here. So that's how we would leverage SPT data. Now, how does this fall in the context of our course? Well, if we're interested in relative density for compaction, then we can use SPT data to tell us whether the relative density has improved. For example, if you have a graph of depth here, and this is relative density, let's say this was before deep dynamic compaction, you're somewhere here, before, and then afterwards, you're here, then you can see the improvement and you can see whether your contractor did a good job. So this is how we make use of in situ testing. Because for very large sites, it's very difficult to take discrete samples, bring it back to the lab. You require boreholes, SPT, borehole, keep on going in depth SPT to get these profiles of depth to compare the effects with and without ground improvement. Now, how about cohesive soils or fine-grained soils? Likewise, we often refer to it in terms of stiffness. So you have very soft clay here, the soft clay, the medium firm, stiff, very stiff to hard clay, with increasing stiffness moving downwards on this table. And we'll hand test here just to help you physically or mentally visualize what type of clay you're looking at. So very soft clay would be like less than 10 kPa, sort of like toothpaste, right? And hard clay would be almost like brick. It's very difficult to indent. And so clay can have very increased stiffness. And if we use an SPT test for clay, notice that these values here are much lower compared to the cohesion soils, right? The granular soils area, because we're working with slightly weaker soils here. And with SPT data for fine-grained and cohesive soils, we can use it to approximate unit weights, right? You can see that the saturated unit weight will generally increase with clay stiffness. Very hard clay, of course, would have a slightly lower saturated unit weight because it's probably quite dry. And also we see that increasing stiffness will lead to increasing unconfined compressive strength for clay as well. So the higher the SPT value, the higher unconfined compressive strength, where you have no confining pressure. It's like a concrete test, right? You make a cylinder, crush it. So that's what unconfined compressive strength is. Or you can get the undrained shear strength. And you can see that with increasing SPT value, you get increasing undrained shear strength. Likewise, there are lots of empirical correlations in the literature. When you work in practice, you'll have to find the ones from relevant projects in Hong Kong or published data that you can use if you only have SPT data, right? And you can see that we have uncorrected lows, you have unconfined compressive strength, clay classification, and clay description. So these graphs here can be used to maximize your SPT data from the test. That's just an example. So that's SPT testing. Now, the next part of in situ evaluation ground improvement is cone penetration testing. Cone penetration testing is mainly for soft soils, such as clays. And we use this approach quite commonly for land reclamation projects to see, for example, if we do field surcharge preloading or we do vacuum preloading, what's the improvement before and after. CPT, if you remember from last lecture, is a static penetration. Well, nothing's really static, quasi-static penetration. We're looking at millimeters per minute. Right? We're not talking about smashing a split spoon or split barrel into the ground. So I feel that SPT and CPT are the most commonly used ones in Hong Kong. So I do want to impress upon you these two approaches because you do have to know how to quantify whether ground improvement is successful. We can probably take a 10-minute break now, and then I'll tie you off with the CPT on that. Let's do that, 10-minute break, and we'll come back. For those of you, your assignment's due today, right? It was due before this class. Please submit. If you forgot, please submit. The Moodle system will be open for another 3 days, I think. And you'll get your second assignment very shortly here. All right, so let's carry on. So the next main in situ testing method I want to discuss, as I mentioned, is the cone penetration test, often referred to as CPT in engineering practice. This method is a quasi-static penetration method, as I mentioned, and mainly used for clay. Now, how does it look like? Let's take a look at the cone. The cone penetration test requires a cone, of course. The cone is shown here. We measure a few things with the cone. In the cone, we like to look at 2 types of stresses. The first one is this cylindrical part here is a sleeve, and there's strain gauges behind it, so you can deduce the frictional stress. So we refer to that as sleeve friction. On these cones, there are also pore pressure water transducers. You don't really have to understand the principle of them, but essentially they're instrumentation to measure pore pressures on the ground. At the tip here, there's a smaller cone where there's likely some strain gauges behind this, or load cells that allow us to measure Q subscript C, which is the tip stress. And often we have to correct the tip stress for the effects of pore pressure. You might be thinking why? Well, normally behind the cone, there's a slight gap here. And then if you have pore pressure, which is isotropic, acting down at the back of the cone, you need to correct it. So it's a pure tip stress or cone resistance. So that's what you see here. It's just a correction factor. CPT testing is highly empirical. You can probably imagine that there's very little analytical method behind it because you cannot really control the drainage condition, and it's difficult to describe the stress path. But nevertheless, these cones are standardized as around 36 millimeters in diameter, and the area, if you look on it for plan view, is about 10 centimeters squared, or you can have a larger cone that's about 44 millimeters and 15 centimeters squared. The pore pressure measurement can be located at any location. Although it's shown just behind the cone here, it can also be put on the tip or just mid-cone as well. It depends. It varies on the type of cone. And there's 2 types of CPTs. One where there's cables. So I mentioned there's all sorts of instrumentation inside these cones. So you can have cables running up, or you can have cableless CPTs where we call these acoustic CPTs, where you just shoot acoustic signal. It reflects and rebounds, and you get measurements, right? So generally, we're referring to ones with cables. And the cables, of course, go to some sort of data logger to give you real-time measurements of sleeve friction, pore pressure, and tip stress. And based on these 3 measurements, you can actually learn a lot about the soil that you're pushing this cone into, especially if you want to understand whether it's improved from field surcharge loading, for example. Now, normally this cone is not very big. What you need to do is you need to attach 1 meter long rods and push it into the ground. And this is usually done inside some sort of truck that provides some sort of reaction to push this cone into the ground. We call this a quasi-static test because the rates of loading are pushed into the ground about 20 millimeters per second, and you take readings every 10 to 50 millimeters. Now, the interesting thing about CPT is it's perhaps the most continuous profile you can get. Do you remember the SPT? SPT, you have to, if you have a plot of land, drill a borehole, and then do the SPT test, and then drill further, do SPT test, drill further, do SPT test. So
if you were to plot a profile of some parameter versus depth, you can only get discrete points, right? With the CPT, you actually get measurements continuously, so you get continuous profiles, which is quite unique about CPT measurements. So from overall view, this is how CPT looks like. Of course, it doesn't have to be a truck. It can be a barge, a ship as well. For example, if you're interested in land reclamation, we can push the CPT in the ground into marine deposits from a barge as well. Inside these CPTs, you can have inclinometers. And what's the point of the inclinometer? Well, it tells you the verticality of your rod, whether you're going in slightly vertical or vertical. So this is an overview of SPT, or CPT. And as I mentioned, there are different types of cones. Hopefully you'll get to see this when you go into practice if you work on land reclamation projects. The CPT cones vary in size. The first three are the standard 36 millimeters. The last one is a slightly larger one at 44 millimeters in diameter. These cones can vary in terms of where the pore pressure measurements are taken. The first cone here has no pore pressure measurement. It just has pure sleeve friction measurement and tip stress. Typically, the sleeve is about 130 to 150 millimeters long. The area for a 36 millimeter diameter cone is standard, 10 centimeters squared. Why do we care about the area? Because we want to know the stress rate. If you want to know the tip stress, you must know the area. So we call this first one a friction type cone pentrometer. And in the second device here, we have a pore stone just behind the cone tip. Pore stones are essentially just some sort of filter to allow water to move in. It's quite pervious, so it can equalize and we can get pore pressure measurements. So as I said, CPT cones can have these pore pressure measurement devices at various locations. In this case here, it's just located behind the cone. You can also have these pore pressure measurements on the cone. And for this larger one, you have also this pore pressure measurement behind the cone. If you want to look at the real photograph of these devices and the various sizes, they look like this. And you would just connect push rods, hydraulic rods, onto the end of it and push it into soft soils. You can imagine that if you run into core stones or granular or gravel soil, you're not going to be able to push this in very well. So it's mostly meant for soft soils. This is a typical cross-section of a cone with pore pressure measurement. So we're not going to get into detail of this, but there are various elements of seals. There are piezoelectric elements. There are strain gauges essentially used to measure sleeve friction, tip stress, and pore pressure. So that's what a typical CPT would look like. Now, some key points I mentioned. Well, this is, of course, historically developed by the Dutch. The advantage of CPT is you get continuous profiles of strength and stiffness. Just like SPT, we can correlate friction, sleeve friction, tip stress, and pore pressure with engineering parameters that are useful for us to assess whether ground improvement was successful. Now, the charm of SPT is perhaps you can, let's say you have a ground like this full of empty marine deposits, and you have lenses of silt. So let's say this is silt, this is sand, this is silt. So the charm of a CPT is as you push it into the ground, you can actually detect these lenses of silt and sand because it's continuous. Whereas if you were boring drill holes, you might flush this out and entirely miss it. So if you look at a continuous profile from CPT readings, you can catch these nice lenses of sands and silt, which might help to explain some geotechnical anomalies on site sometimes. So that's the charm of a continuous profile. You can also use CPTs for not just geotechnical applications, but for environmental applications. You can measure the pH. You can measure other environmental parameters for site characterization as well, and the discontinuous lenses, as I just mentioned. CPT probes are generally 36 millimeters diameter with a cross-sectional head of 10 centimeters squared. The typical shape of the cone, it has a 60-degree apex. So the apex is this 60-degree apex. And I showed you other configurations, but the most commonly used one is this 36 millimeter diameter, 10 centimeters squared, 60-degree apex. And the typical loading rate is about 10 to 20 millimeters per second, so it's quite slow. So it's a quasi-static test. It's a penetration test, but quasi-static. The cone penetrometer that I showed you is heavily instrumented. You have low cells, which are strain gauges, over strain gauges, to measure sleeve, friction, tip stress. And you can also have piezoelectric elements to get the pore pressure. So these are just fancy words for measuring pore pressure, sleeve friction, and tip stress. And we'll talk about how we use these measured parameters to get geotechnical properties. Other important points that I want to bring up, there are different names for CPT. If they can be used to measure pore pressure, you might see them called piezo cells as well. Some CPTs that measure pore pressure are also called CPTU. The U is, of course, for pore pressure. The presence of pore pressure measurement is quite useful. Sometimes you can hold the CPT at a particular depth, and when you push it in, you'll generate excess pore pressures, right? You can hold it and see how long it takes to dissipate these pore pressures, right? Then you can estimate the permeability of the soil. You can even use it to get consolidation parameters. So think about how. If you do this in situ, it's quite useful. As I mentioned, it can be quite useful for environmental assessments. You can get gamma. Gamma is very similar to nuclear densometer when we talk about compaction. You can shoot gamma waves rays up to see the degree of compaction as well. You get pH, salinity, and temperature. You can install all these onto your probes. These are quite versatile. You can put these onto barges or ships, so you can get offshore marine deposit strength and stiffness profiles as well. And cone resistance can be correlated, it's empirical, can be correlated to bearing capacity, density, and strength parameters as well. The core limitation of CPT is perhaps if you run into very granular material, core stones, boulders, then you're not going to be able to push it through, then you have to extract, find another location, and penetrate further. This CPT test, as we discussed quite a bit, is quite suitable for marine deposits, for land reclamation, but you won't see this being used for CDG slopes or granular material, or weathered rocks of Hong Kong. To show you some realistic pictures of it, this is a Fugro truck for mobile CPT testing. It can be jacked up, provide a bit of reaction. Inside these trucks is a frame to provide reaction to push this cone in. You don't need a lot often. So this is the truck. It can be stabilized with these stabilizers. Inside there's a loading frame. These are 1 meter rods. You can just keep on attaching with the threads, the 1 meter rods on, and the cables will come out to give you real-time data acquisition for friction, tip stress, and pore pressure response. And you can see that this is the rod coming out from under the truck here into the ground. So that's typically what happens, and you can have some sort of user interface for data acquisition, which is often in terms of depth. So you can get those parameters that I mentioned in terms of depth. Now for CPT testing, what can we measure? Well, we can measure verticality. There are inclinometers inside these cones. We can get pore pressure with piezo cones, as I talked about, soil resistivity, can give you indications of permeability or environmental parameters. You can also use it for PPV, ground vibration. Geophones, same thing as when we carry out very dynamic things on site. We usually measure the PPV, particle velocity, using geophones. We can use gamma ray backscatter for density. Remember the compaction lecture, we talked about backscattering for nuclear densometer. Some devices can also give you pressurometer values. What is that? Well, some devices can actually expand. If you expand, what can you get? Well, you can probably get K0 values at reference pressure as well. Compressibility as well. If there's an element that can expand, you can do acoustic penetrometer. So geophysics means you can send a wave, see how long it takes to reflect back. If you know the speed of the wave, you know the distance, you know the time, then you can use it to do something such as the shear modulus and so on. Right? So there are various things that CPT can measure. It's quite versatile, as you can see. And as I mentioned, there's also CPTU or piezo cones, more or less the same thing. Piezo cones can be quite useful by getting pore pressure response. The first is the advantage of having pore pressure measurements is detecting the thin layers of silt and sand I talked about. Now, how do you do that? Well, if you have a thin layer of sand, the permeability will definitely be more pervious compared to the clay. So leading up to this lens of sand, you'll see pore pressures drop because of the higher permeability. So you're looking at a continuous pore pressure profile. You'll see it drop suddenly as it passes the lens of sand, and that can be used for profiling. You can use that to identify thin layers of sand and silt. Likewise, if you can hold a CPT with pore pressure measurement at a particular depth, you can deduce the permeability. If you know the permeability, you can guess what type of solid it is. Well, we talked about 10 to the minus 3 meters per second is probably coarse grained material, 10 to the minus 9 and less is probably clay, and something between silt, right? So you can use that to determine the soil type. You can also get static pore pressure. So you want to know what's the in situ pore pressure. It could be an excess, it could be hydrostatic. You just hold the probe there, as I mentioned, and you can deliberately wait for pore pressures to dissipate. When you push the cone in the ground, you will generate excess pore pressures. And if you wait for it to dissipate, you can treat this like a permeability measurement, or you can treat it like a odometer or consolidation related parameters. And that's point 4, essentially. You can get the coefficient of consolidation if you know permeability. So that's the